Hi there, this is Jude Socrates. Welcome to today's video, which is a continuation of our previous video where we learned two methods, the trapezoidal method and Simpson's rule, to approximate the value of a definite integral. So in today's video, we're going to go back to those two methods and we're going to analyze the error that we get when we use those methods. So we are going to basically ask a couple of questions for each problem. There you go. Now you can see them in their entirety. What is the maximum error that we get if we apply one of the methods to approximate a definite integral using n subintervals? So in our two examples, we used 8 subintervals, n equals 8. We got good answers. They were in agreement with what Maple got to 2 or 3 decimal places. But we still want to know, well, can we be more specific about what is this error that we get? Is it 0.001, 0.00001? Just how big is the error that we get from these methods? And if everything is fair, well, if we increase the number of subintervals, then the error should, of course, also get smaller. It's only fair, right? If you work harder to plug in more numbers, instead of n equals 8, how about n equals 20? Then you should be getting a more accurate answer. So we're going to see, given n and other parameters, what is the maximum error that we get from each method? So this, the second question that we're going to ask is, thank goodness for the pause button. The second question that we're going to ask is, if you want a maximum error which is a certain amount, okay, so for example, you're not happy with your error because, oh, it's only accurate to 0.0001, okay? That's not good enough for you, let's say, or your boss, more importantly. So how can we make the error even smaller? Well, we raise the number of subintervals. And if your boss says, well, I want the error to be no bigger than a certain amount, 0.000000001, okay? Put as many zeros as you want over there, okay? So it's now up to you to find, okay, how many subintervals will we need? What is the least number of subintervals that we are going to need for each method? And of course, in practice, as I mentioned in the previous video, you're not going to do this by hand or even by calculator. You're going to have a computer, a spreadsheet, doing this for you. Okay, so it doesn't matter if you need 100 subintervals or 2,000. You might need to go on a coffee break, and by the time you get back, the computer has what you want, okay? But it's really up to you to compute. Okay, how can I find the least number of subintervals that will guarantee a maximum error of a certain amount, and how can I justify it to my boss or your teacher? So, in order to study those two problems, we will need some notation. We are given a fixed integral from a to b of f of x dx, and we denote by capital I for integral, the exact value of this definite integral, okay? So if we were in an earlier video, maybe that exact value will be pi over 2 or square root of 5 or whatever. There's an exact value. What we found in the last video were approximations for this integral. Okay, so we got two answers. For the trapezoid method, we will write t sub n to be the approximation that we get when we use the trapezoid method using n subintervals. Okay, so t sub 8 was the first answer that we got in the previous video. Similarly, we will denote by s sub n the approximation that we get when we use Simpson's method with n subintervals. So in our last example, we got s sub 8 since we used 8 subintervals for Simpson's method. Now, the error is in almost any scientific discipline. The error is usually, almost always, the exact answer minus the approximation. So E sub Tn will be the error for the trapezoid method using n subintervals. It will be the exact answer I minus the approximation. So as it is, it could be positive or negative. If our approximation is slightly less than the exact answer, then this will be a positive number. Or maybe it's slightly more, then this will be a negative number. So similarly for E sub Sn, the error that we will get when we apply Simpson's method to this definite integral using n subintervals. So here's the theorem that is going to tell us just how big is the error for the trapezoidal method. There will be a similar error formula for the Simpson's rule. So suppose that k is a positive number such that the absolute value of the second derivative of our integrand f of x is at most k for all x which is within the interval of integration from a to b. If E sub Tn is the error that we get using the trapezoid method, using the notation that we defined above, then the absolute value of E sub Tn is at most this positive number k times the width of the interval b minus a cubed divided by 12 n squared, where n is the number of subintervals that we use to approximate our integral. And if you're wondering, where did that come from and can you show me the proof? This comes from a field of mathematics called numerical analysis, and we are not going to go over the proof. I don't know how to prove it. We are going to apply it though, so that number one, how can we solve for this value of k? And how can we use this formula to answer the two questions that we asked above? So obviously, the hard part about applying the formula that we just saw is finding this number k, this positive number k. Usually, in a first semester calculus course, we take a function and you remember the extreme value theorem, where we look for the maximum and the minimum value of a function on a closed interval if your function is continuous. That's always possible. So definitely the absolute maximum of the absolute value, so many absolutes, the absolute value of the second derivative constricted to this interval would be a legitimate value for k. But any number bigger than this maximum value will also work. Okay, so if you know that your second derivative in absolute value is at most 5, then k can also be 10. Okay, so any number bigger than that maximum value is going to work. Okay. However, we don't have to work that hard because to do the extreme value theorem, you have to take another derivative, set it equal to 0, find the critical points, too much work, okay? All we need is any positive number so that the absolute value of the second derivative is at most that number. That's all we need, okay? So what we're going to do has almost no calculus involved except for monotonicity. Okay, but there is some serious math going on. Here are some tricks that can help us to control the absolute value of the second derivative. Okay, so the most important of these is probably something that you've never seen before, or if you have, maybe just once or twice. It's called the triangle inequality. It says, if you're adding or subtracting any two numbers, real numbers, then the absolute value of that sum or difference is at most the sum of the absolute value of those two numbers. It's So let's think about that for just a little bit. Okay, why is that true? Well, if A and B are both positive, like 2 and 3, okay, something simple. Well, 2 plus 3 is 5, so the absolute value of 5 is, in fact, equal to the absolute value of 2 plus the absolute value of 3. All of it's positive. Okay? Same thing if they're both negative. Okay, so if you have negative 2 plus negative 3, you'll get negative 5. And the absolute value of negative 5 is again 5, which is again the sum of the absolute value of negative 2 and the absolute value of negative 3. That's again 2 plus 3. So when A and B are both positive or both negative, that's not even an inequality, that's actually an equation. The tricky part is when they're different signs. Okay, so yeah, maybe let's demonstrate it over here. If A is negative 2 and B is positive 3, okay, so one is negative, one is positive. If you add them together, you're going to get 1. But the absolute value of negative 2 is, again, positive 2. The absolute value of 3 is positive 3. So on the left side, you will get 1. And on the right side, you're going to get 2 plus 3. Is it true that 1 is less than or equal to 2 plus 3? Yes, of course that's true. Okay. So to be safe, when we expand the absolute value of the second derivative later on using the triangle inequality, we will always put a plus sign between two absolute values. We're going to see examples where there will be negatives inside, several terms added or subtracted together. The key idea is simply change all the minuses into plus, okay? Make all the minuses go away. Easy way to remember this, when you're taking an absolute value of a negative, it turns into a positive. Okay, so all negatives must go away. If you're adding or subtracting, turn it all into pluses. Okay, what else do we know? Well, we know properties of absolute values. So if you multiply two numbers, the absolute value of the product is equal to the product of the absolute values. Same for a quotient, of course, b cannot be 0. You already know that. We dealt with cosine 1 over x, so we also know that the absolute value of the sine function, sine of anything, is at most 1. Cosine of anything is at most 1. Okay, monotonicity. So this is a particular instance of monotonicity. If x is between two positive numbers, a and b, then the reciprocal of x is between 1 over b as a smaller value and 1 over a as a bigger value. Okay, if you take the reciprocal of a number, the reciprocal of a bigger number is smaller than the reciprocal of a smaller number. For example, if you had 2 and 3, you will have 1/2 and 1/3. But who is smaller, 1/2 or 1/3? It's 1/3. 1 over x will be between 1/3 and 1/2. Okay? All right, so more generally, if you have a monotonic increasing function on your domain, then the highest value of your function will happen at b. So g of x will be at most g of b for every x in your domain from a to b. And similarly, if you have a monotonic decreasing function, then the highest value will occur at the left endpoint. So your function is at most g at the left endpoint, a. So we're going to use these properties and, of course, general arithmetic in order to control the second derivative of our function. All right, here we go. So in the last video, we approximated the definite integral from 2 to 6 of cosine 1 over x dx. We got something like 3.8. We want to know now, what is maximum value for the error that we got when we applied the trapezoid method using 8 subintervals. So again, the hard part of applying the formula that we will use is to finding this value for k for the second derivative. Okay, find a value for k for that the second derivative is at most this positive number k. So to save time, right, I got the second derivative using Maple. You can also do it by hand. 2 derivatives is not so bad. When we get the Simpson's rule, we're going to need 4 derivatives. So we needed this anyway. Okay, so we want to control the absolute value of the second derivative. Right, so let's get started. We want to control the absolute value of the second derivative. All right, so I'm going to copy the symbol in here. Okay, so we know that this is our second derivative. Excuse me, too many pastes. And well, first thing we'll do is we will wrap this second derivative in absolute values. Okay, so we're going to take this and we're going to put it in there. Okay, so, well, you know what? These are both negatives. So the absolute value of negative something is the same as the absolute value of the positive equivalent. So we can turn that into a plus and that minus into a plus. Okay, fine. But we are now going to apply the triangle inequality. Okay, so there are 2 terms inside the absolute value. We are going to distribute, so to speak, that absolute value, but it's not going to be an equal sign anymore. It's going to be a less than or equal according to the triangle inequality. Okay, so we're going to break up this. I'm going to make 2 copies because we are going to add them together. Right, so the first absolute value will contain the first term. The second absolute value will contain the second term. Let me get out of the way here. Okay. So the absolute value of the sum of these 2 things is at most the sum of the absolute value of the individual terms. Great. So now, well, we can use the product and quotient rules for absolute values. Okay. So now we can turn each. Okay, well, this is a quotient, so I can turn it into a quotient of absolute values. Right, so I can put absolute value of cosine 1 over x in the numerator by itself. So I will edit this. Okay, I will take this out. There we go. And in the denominator, I will have absolute value of x to the 4th. So let me fetch my absolute value symbols here. In the denominator, I have absolute value of x to the 4th power. Ta-da! Okay. So we are going to do something similar to the second term. It is a product and a quotient, but of course the 2 can go out. Okay. And instead of cosine 1 over x, I will have sine of 1 over x in the numerator, x cubed in the denominator. So let me just copy that here. I will turn cosine into sine, and x to the 4th will be x cubed. All right, there we go. So now, I have 4 absolute values, and everything is positive. Okay, so notice that's a +2. The minuses are gone, long gone. So what did we say? The cosine of anything is at most 1. The sine of anything is at most 1. So now the next step will be a less than or equal to I can replace the numerator with 1 because cosine is at most 1. And similarly for the second, I can replace the numerator by 1. Okay, there we go. What's our interval again? Let's go back here. Our integral is from 2 to 6. Okay, so x is between 2 and 6. 2 less than or equal to, where are you? I know you're here. X less than or equal to 6. Okay, so x is positive, right? So we can replace this with just equal to 1 over x to the 4th plus 2 times 1/2 x cubed. Yeah, our domain is a positive set of positive numbers, so we don't need the absolute values. Okay. However, we do have reciprocals. Okay. So what did we say? If you take the reciprocal of a number, the endpoints switch in location. So the smallest number is 1/6. The biggest number is 1/2. Right? So 1/6 less than or equal to 1 over x and less than or equal to 1/2. So let me put a couple of less than or equals here, and let me borrow this. Okay, 1 over x will be between 1/6 on the left and 1/2 on the right. Okay, so what does that mean? Well, let's think of more properties now. We want x to the 4th power. Okay, so x to the 4th, that means we're going to raise this to the 4th power, and everything is positive. Let's again exploit monotonicity. X to the 4th is now an increasing function. Okay, so therefore 1 over x to the 4th will be between 1 over 6 to the 4th and 1/2 to the 4th. So we have this same inequality. I will copy the end because I will have one more. Oops. Okay, scroll down too fast. So I want 1 over x to the 4th. I also want 1 over x cubed. So 1 over x to the 4th will be between 1 over 6 to the 4th and 1 over 2 to the 4th. And similarly, 1 over x cubed will be between 1 over 6 to the 3rd power and 1 over 2 to the 3rd power. All right, but look at the trend here. Equal, equal, less than or equal to, equal, less than or equal to, equal. The numbers are getting bigger. Okay, these are the same, and now we're going to make it, maybe it's a little bigger. Now it's the same, maybe it's a little bigger. So now, our next step is, okay, we're going to use these inequalities, but I want the less than or equal to. Okay, 1 over x to the 4th is less than or equal to 1 over 2 to the 4th, and I have the plus 2, 1 over x cubed. 1 over x cubed is at most 1 over 2 cubed. There you go. So now these are all just numbers. What is that equal to? That is 0.3125. Okay, so this it's exactly actually 0.3125, not even an approximation. The second derivative in absolute value is at most 0.3125. And that's good because our k is going to appear in the error formula in the numerator. So the smaller the value of k, the smaller the error that we're going to get. Okay, so it's time for us to apply our formula. All right, so I made a copy of the theorem so we can refer to it. We have found the value of k, 0.3125. Any number bigger than 0.3125 will also work, okay? But we might as well use that same number. So the theorem says, if k is a positive number, this guy, so that the absolute value of the second derivative is at most k for every number between a and b. If e sub tn is the error that we get using the trapezoid method, then the absolute value of the trapezoid method error is at most the number k multiplied by b minus a cubed, the width of our interval, cubed, divided by 12n squared. All right, so we are ready. Copy this formula. Let's move it up here. Okay, so what do we have in this formula? Okay, so we know that n is 8, so let's change that 8. And we know that our k is 0.3125 because we worked for it using the triangle inequality and other tricks. Our a and b are 2 and 6, so 6 minus 2 cubed. 12n squared, so our n is 8 subintervals. So 12 times 8 squared, or 64. All right, so yeah, so the rest is arithmetic. We will need 4 cubed, 6 minus 2 is 4, and 8 squared is 64. Oh, check it out. 4 cubed is 64, 8 squared is also 64. So those just cancel out. 16, yeah, they just cancel out. So that goes away together with this. And so the maximum error that we get is, come on, equal to, oh, okay. It's about approximately, how many zeros do we need? 0. Equals 0.0260416666666. Okay, so yeah, that's actually an exact decimal because we're dividing by 3 and 4. Okay, so that is the maximum error that we will get, that we got actually. We can now say with confidence that the maximum error of our answer in the last video, in that first example, is at most 0.026, or if you like, you can even say it's at most 0.03. Okay, you can give an answer slightly bigger than this, but not smaller. You can't say that the error is at most 0.02. Nope, that's a 6 over there. So you can say it's at most 0.03, but not 0.02. Okay, no cheating. All right, 0.03, that is not, I don't know about you, but that does not give me a lot of confidence about this answer that we got, even though it was pretty darn close to what Maple got. And of course, Maple is always right. No, just kidding. So now, follow-up question. Into how many intervals, subintervals n, should we subdivide 2 to 6 so that the error is at most 0.000001? Okay, 0 to me, I don't know, that's a little too big for my taste. So let's make it a lot smaller. I want a really accurate error, so accurate that the error is at most this really tiny, tiny number. Okay? So let's go back to the formula. So where are you? It's right here in the blue. So the formula says that the error is at most this much. I want the error to be at most this much. So to accomplish that, the easy thing to do is to make this number smaller than this number. Okay, think about the transitive property. If A is less than or equal to B and B is less than or equal to C, then A is less than or equal to C. Okay, so that will give us what we want. To achieve this goal, we can force the error, which we know is at most that, by the formula, to be at most this tolerance. Think of this as a tolerance. I can tolerate an error of at most 0.0000001. No bigger than that. Okay, so what do we know in this formula? We already got the K, correct? I believe it was 0.3125. So there it is, 0.3125. And we have the same interval, 2 to 6. So again, that's 4 cubed. Okay? But now we don't know the n. Okay, that is what we are solving for. In how many subintervals should we subdivide 2 to 6? Okay, so we must solve the inequality, which would be, so this is what we want, and our K is 0.3125, and our B minus A, again, is 6 minus 2. We must solve that inequality for n. And that is our goal. All right, so what are we going to do? Well, I guess we can simplify that first. What is 0.3125 times 4 cubed, 64. Okay, so this time it doesn't cancel. All right, we knew that n was 8 before, so it could cancel. So, oh, it's exactly 20. But we want over 12. No, you know what? Let's just keep it as 20. So we get 20 over 12n squared is at most 0.00 blah, 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 1. Okay, we are solving an inequality, not an equation. Well, let's isolate n. So, something to remember, if you're multiplying or dividing an inequality, you have to be careful with positive and negative numbers. Okay? N is a positive number. We are we're subdividing an interval into an n number of pieces. So n had better be positive. Okay? Similarly, this tolerance is positive. So when we multiply or divide by positive numbers, the inequality does not flip. Okay? So this inequality is the same as move the n squared to the other side. Maybe we'll write it that way. Okay? And last step, not quite last step, we can move the tolerance to the denominator on the left. Divide both sides by this teeny tiny number. There we go. Ooh, if you divide by a small number, it's going to be a big number. So what is this approximately? Yeah, that's a big number. So the left side is this much. So n, that should be less than or equal to n squared. Yeah, we can remove those parentheses now. Okay, well, again, n is positive, so we can take the square root of both sides. In other words, raised to the power 1/2. This to the power 1/2 square root is less than or equal to it. There we go. So let's approximate that. What is this? Big number. So this should be less than or equal to n. All right, but remember, n is an integer. It's a whole number. It has to be at least 4,082 and 48 cents. So what does that mean? What is the smallest value that n can achieve? N has to be at least, let's write it more naturally, as at least 4,081, 82, or 83. Those are your three choices. Which one should it be? I hope you answered 4,083. N has to be a whole number bigger than that number. The smallest whole number bigger than that number is 4,083. If you said 4,084, sure, that also works. But this is the smallest integer that you would have to subdivide that interval in order to get an accuracy of at most this really small amount. Okay? So again, of course, you're not going to do this by hand. It took us like 10 minutes to do that example with a hand calculator or Maple. You will make a spreadsheet or something, or a computer program that will do this a lot more efficiently with more than 4,000 subintervals. All right, so now we want a similar theorem for Simpson's rule, and it goes like this. This time, suppose that j is a positive number, so that the absolute value of the fourth derivative, not just second, but the fourth derivative of the integrand is at most j for all numbers inside the interval of integration. And if E sub Sn is the error using the maximum error using Simpson's rule, as we put in our notations above, then the absolute value of this error is at most the j that we get for the fourth derivative times the width of the interval, b minus a, this time raised to the fifth power. Last time it was to the third power. Now it's fifth power. Divided by 180 times n to the fourth. Okay, before it was 12n squared. Now it is 180 n to the fourth. So, of course, the tricks that we need to find j and to manipulate this inequality are very similar to what we had for the trapezoid method. All right, so for Simpson's, we went through the same definite integral, same number of subintervals, 8, and now we want to control the error. This is the fourth derivative of cosine of 1 over x. All right, so again, to save time, we have the second derivative, take the derivative 2 more times. We want to control the absolute value of this fourth derivative. Okay, so we're going to do something very similar to what we had for trapezoid. We are going to take the absolute value of the fourth, which is the absolute value of all of this. Okay, get out of the way. Now we have some serious triangle inequality to apply. Right? So notice that there are 2 positive and 2 negative terms. Right? So the triangle inequality obviously generalizes to 3, 4, as many terms as you want. The idea is simple. Turn all the negatives into positive. That's all you have to remember. But also, maybe I shouldn't say that too quickly, that equation will now turn into an inequality because of the triangle inequality. It will now turn into a less than or equal to. Okay, so we will break this up into 4 pieces. So let me do it a little bit at a time. So the first one gets only the first term. The second one gets only the second term. But you know, to save some time, why don't I do this? Haha. Let me make a copy of that, and now I will remove these two, so I only have the second term there, and I will remove this here. I have these two terms, so I will make one more copy. Little tricks that I have learned, and I will keep the third term there and the fourth term there. Let's take a pause to look at what we've done. We have broken up this single absolute value into 4 absolute values. All the minuses, the 2 minuses, are gone, turned into plus because of the triangle inequality. Okay? So now we can apply the product and quotient properties of absolute values like we did for trapezoid, and we can take the 12 out over here. We can take the 36 out over here. We can take the 24 out. Okay. So that's the product property for absolute values. And now what? Well, we can apply the quotient property, but in the numerator, we simply have sine or cosine. Okay, so remember what we did last time. The biggest value for sine and cosine is 1. So we can replace all of the numerators by 1, but that's no longer an equation, that's an inequality. Less than or equal to absolute value of 1 over x to the 8, 1 over x to the 7 times 12, 1 over x to the 6 times 36, 1 over x to the 5 times 24. Ooh! All the trig is gone. Goodbye. All the minuses are gone. Turn to plus. Okay, so we lost them in the first step. Okay, so yeah, we start out with something nasty and complicated, but this is not so bad, right? And all we have to do is build on what we did last time, because we said x is between 2 and 6. 1 over x is between 1/6 and 1/2. All right, and what did we notice? 1 over x to the, what was it, third power is at most 1/2 to the third power, and 1 over x to the fourth power is at most 1/2 to the fourth power. Okay, so we can replace x here with just 2, because 1/2 is the biggest value of 1 over x in this interval. Okay, so I can replace our x with just 2 and 2, get back here, and 2 here, and 2 here. There you go. All the x's are gone, and we simply have numbers. So can Maple find this for us? What do we get? 1.41. So that is bigger than the k that we saw for trapezoid, but that's all right, because in the formula for the error, we do have bigger numbers in the denominator. Okay, so let's bring back that formula. All we need is the formula over here. So let's bring it back. Here is our E sub Sn, and there we go. All right, so we have our J. Our J is this much. Same domain, 2 to 6. So this is again 6 minus 2 to the 5th. And you might say, oh, that's much bigger now. Yeah, that's 5th power. But our m is 8 to the 4th power. So yeah, there is a fight going on here. Okay, that's a 5th. That's big. This is also big. Okay, so do we get a good error? We get, oh, okay. Before it was something to the minus 2. Okay, so this is slightly smaller than the error that we got for the trapezoid method, right? So that is the maximum error, approximately. I would just put equals there, even though that should be the approximate symbol. All right. All right, our final problem for the day, similar to what we asked for the trapezoid method. Into how many subintervals n should we subdivide 2 to 6, our domain, so that the error is at most this teeny tiny number? So for trapezoid, we got something like 4,082 subintervals. And let's see if Simpson's will do much better. It would be nice if it were under 1,000. Let's see. So here is the formula for the error. And again, to accomplish this, to make the error at most 0.001, you make this less than or equal to this tiny amount. So to accomplish this, we must solve this. That's my dog. There's someone at the door. All right, there we go. So we want this to be at most our tolerance. Make this less than or equal to 0.001. Solve this inequality for n, just like before. All right, so we have our j. So let's copy this. And our j is this much. So turn j into that. b minus a, 6 minus 2 to the 5. And 180, we don't know n. And that's a constant on the other side. So remember what we did last time. We simply switched. Basically just switched the n and this number. Everything is again positive. So we can copy this, and that will be less than or equal to, on the other side, n to the 4th power. Bring the n to the 4th power to the right. This will go in the denominator on the left. Okay, there we go. So n to the 4th will have to be at least this amount. So let us compute this number. It is approximately, another big number. Yikes. So earlier, it was something like that, but it was n squared last time for trapezoid. Okay. So therefore, we'll now switch this around. N has to be at least the 7th root. Okay, so before it was square root. Now, I'm sorry, it's the 4th root, not the 7th root. I was looking at n to the 7. Nope, only 1/4. 4th root. Okay, so what is that approximately? Oh, I'm sorry. Maple does not like brackets. It has to be parentheses. Would have said, what a point. Ooh, look at that. It's only about, approximately, although I will put an equals there, 94 point blah, blah, blah. This much. Okay, so now, for the trapezoid method, we simply rounded it up to the next higher integer. However, this is Simpson's. Don't forget that for Simpson's, the number of subintervals has to be even. Okay? For Simpsons, n must be even. And so the smallest value for n must be, so now your guesses are 92, 94, or 96. I hope that you answered 96. It has to be an even number bigger than 94.6. 95 is not even, so it must be 96. All right, so that is how many subintervals we'll have to subdivide our domain. That's a lot smaller than 4,000 and something. Okay, great. So I hope you enjoy the video, and until next time, enjoy the rest of your day. Bye.